Yeah, so recording has started. So let us start for today's lecture. Any question before we start? Fine.
Sir,
Okay. Yes, please. Please.
sir,
Your voice is breaking. Hello?
previous is that in our syllabus? Yes.
Uh, can you repeat again, please?
Sir, yesterday in the class you taught about the Borel set.
No, no,
Is
no.
that in
That
our
is not in
syllabus?
the, no, no. That is not in our syllabus. Just to
Okay.
give you the idea that if our set sample space is not countable, then what will happen? Then we can not define the measure function. So that is, you just forget it. I mean, for our purpose, we just have this sample space to be finite or countably infinite. Okay.
Okay.
Okay. So let me start. So just to recap what we have so far, we have discussed the we have started with the E. E is the random variable. Sorry, random experiment. So what do you mean by random experiment? We say experiment is random if we have three properties on that. Like first one is if we know all possible outcomes is known, and then second thing is if we cannot predict which outcome will occur before we do the experiment, outcome are not predictable before doing the experiment. And the third one is we should able to repeat the experiment as many times as we want, at least conceptually, so theoretically. So that is required for some of the cases. So that is if that is called random experiment. For example, if you are tossing a coin, that is one example of random experiment. If we are tossing a coin, then we have two outcomes, H or tail, that we know, outcome we know, all possible outcome we know. That is the first condition. And second condition is we don't know which outcome will occur before we toss the coin. Before we toss the coin, we cannot guarantee that, okay, head will occur, tail will occur. So that is not possible for random experiment. And we should be able to toss the coin repeatedly like that. Okay. Then we have defined what is called sample space, that is omega we define. So, and we have sample space is basically set of all possible outcomes of the experiment, set of all possible outcomes of our experiment. Okay, that we put in a set, and then that set is called sample space. For example, if we are tossing a coin, then our sample space is H and T. We have only two outcomes, H and T. So now this thing we have discussed, that if this could be finite or infinite. If it is infinite, then either it will be countable or uncountable. So if it is countable, up to countable, we can just for our syllabus we have only up to countable. So in that case, we can take any subset of events. How we define any subset of omega, any subset of omega is an event. So, for all subset of omega is event. That is how we define the event. Now, as we mentioned the Borel set, so the yesterday's class we have little bit mentioned about this. So if this is uncountable, then we can define this events as a member of a collection. That collection follows some properties, like if A is if A is belongs to that collection, then A complement will belongs to that, and then this is one property. And then if we have a1, a2, an, this is up to infinite, then the union is also belongs to that collection. And then this omega, the sample space, I mean not in terms of omega anyway. So then we say this collection is a Borel set or sigma field. Then, but if our sample space is countable, then we can easily prove that this is a sigma field, because if we take any subsets and if we take finite countable union of that subset, that will be again a member of the power set or subset. Then that is belongs to that is again a subset. So that is belongs to power set. So that is basically a Borel set. Okay. So, but anyway, we just define the even as any subset of omega, because our purpose we are just considering the sample space is either finite or countably infinite. So, any subset of omega is an event. So, basically, the set of all events is our power set of omega. If we can define the, I mean, if it is finite or countably infinite.
So what is the third condition
So
that you have
then,
defined?
which one?
Sir, in this, if A belongs to delta, then what is the third condition that you have defined in this case?
Where?
It isn't. So the third condition, it isn't really legible from here. I can't understand.
No, I didn't get you. Can you repeat again?
So can you repeat the conditions of the it being inside, like an event inside the Borel set?
Yeah, that whole set belongs to this. I mean, if we are constructing the Borel set over a say set S, or here in our case sigma, then the actually this is first condition, that S will be a member of that. Okay, that is that is that you can say that is the first condition. Then the this if A belongs to this collection, then A complement will belongs to this collection. And if we have a a collection of A1, A2, An, then we have the union is also belongs to this. Okay. So here we are talking about omega. So in terms of, so this is omega must belongs to this. So
Sir,
this,
so
yes.
can you explain what's a sigma field?
Yeah, this is the sigma field. We define sigma field over a set. Over a set, if this is having, so Borel set, Borel set, over a set. Here set is our omega. So how we can define? We call this is sigma field if it satisfies these three property. So sorry, if it satisfies these three property, that omega belongs to, so we call this field to be this symbol. And then if A is belongs to, then A complement must belongs to this. And if we have a A1, A2 dot infinite collection, then we have AI, either it is finite or infinite. It belongs to, if all this belongs to this delta, then if this condition satisfy, then we call this delta is a sigma field. Okay. Now if our omega is finite or countably infinite, if our omega is countable, then we can easily show that this all the conditions is satisfied. So in that case, we have no problem with that. Okay. And but the other thing, if it's not if it is uncountable, then you have to carefully define that. so that we can define the probability measure on that. Anyway, but this is
And sir, what is delta here?
delta is the, we are talking about some collection. Delta is a collection which is a subset of this set omega. Some collection we want to, but for our case delta is basically power set, which this one, na? This is a, for our case is power set of omega, because we are dealing with countable this thing. But anyway, you just for our syllabus we don't have this sigma field, all this thing, just to, you must have seen this in some of the books, so I wanted to just give you the rough idea. Okay, so
Okay, sir.
yeah, so let us just proceed to defining the probability of an event. So far we have done this E is the random experiment, and we have this collection of all possible outcomes, that is our sample space, and we have defined the event. Event is any subset of this power set. I mean, any subset of this omega is an event, so that is a member of this power set, you can say. So, and then we define two probability definition we have discussed in the last class. One is classical definition. So for that we have to assume this omega to be, this sample space is finite, we have finite number of outcomes, and then they are, all the outcomes, simple outcomes are equally likely. So equally likely we have to define properly, because we have not yet, so that means chances of getting each of these are equal. So then we call equally likely. Then we have defined the probability of an event A as this, probability of A is cardinality of A by cardinality of omega. Sorry. Cardinality of A by cardinality of omega. So this is the classical definition we have discussed yesterday. Classical definition of probability. Okay, so this has a drawback. We have to assume all the outcomes are equally likely. Also, this will not work if the sample space is infinite. So then we have another definition which we discussed yesterday, that frequency definition. Frequency definition of probability. So for this reason, you need to repeat the experiment many times. So now we repeat the experiment many times, and we just observe this ratio, number of times number of times this, we are defining probability of A. So number of times this A is occurring, we just count that and divided by number of times this, number of times we are doing the experiment. So this will eventually convert to a fixed number as we run the experiment many times. Theoretically is n tending to infinity, like, so number of times we are doing the experiment, then this will convert to a number, fixed number, and that fixed number we define to be the probability of the event A. So this is a this will fix to a number. This is statistical phenomena. So that that for that reason you need to repeat the experiment quite number of times. So that is the another problem with that, because we may not, some of the experiment may not be repeated. So up to this we have discussed. So now we will talk about the another definition of which is more powerful definition of probability, which is called axiomatic definitions, which has some rules. Based on that rules we will define the probability. So that is axiomatic definition of probability. Probability. Okay, so for that we have to just have some rules or axioms. So E is our experiment, this is our sample space, and if we assume the sample space is finite or countably infinite, so this is our any member of the power set is an event. So this is set of all possible subsets. So any subset is an event. Now we are going to define, we take a subset of omega, and then we are going to define the probability of A. So we defined using the three rules. So the rule number 1 is for all probability of A must be a positive number. So here we are going to define probability as a function from this set of all possible I mean on the events, say power set from the to the real numbers. Probability is a real number. So we just take a from this. So this is for all events. This is first rule. So probability is a positive quantity, non-zero, non-negative quantity. So this is the rule number 1. So for all A, we have probability of A must be greater than or equal to 0. And rule number 2, probability of omega. So omega is also a subset of this. So we can define the probability function or probability measure on the omega. So omega, this is 1. This is what is we call certain event. Probability of omega must 1. And then we have a collection of mutually exclusive events. Either this collection will be finite or infinite. We have a collection of mutually exclusive events. Either it is finite or we have an infinite collection, but countably infinite collection we have. Then these are all subset of omega. So these are all events. Only we can define the probability on the events. So everything must be belongs to power set of omega. So then rule number 3 is telling then the probability of then we can take the union of this, either finite union or infinite union. If it is finite union, then up to n. So this is also an event because union this is also a subset of omega. So this is also an event. If this is also an event, then we can talk about probability of this. So probability of this, they are mutually exclusive. Mutually exclusive means AI and AJ, they are disjoint. I mean, they are not overlapping. If this is AI, then AJ must be here, something like that. Set diagram. So this is for all I not equal to j. So for all I not equal to j, if they are mutually exclusive, they have no common points, their intersection is null, then we can write this as sum of their probabilities. Probability of A1 plus probability of A2 dot plus probability of AN. Okay. And this is true for infinite collection also. So if we write this in symbolically, probability union of I is equal to 1 to infinity. This should be written as summation of probability of I is equal to 1 to infinity. So this is an infinite collection of mutually exclusive set of events. Then we have this rule number 3. So if any such function p satisfy these 3 rules, then we call this is a probability measure or probability function. And from now onwards, yes, please.
Sir,
Yes, please.
In definition of function, like you defined the p function from power set of omega to r. Instead of r, there should be sigma omega
No, it
or
is
sigma.
this is codomain. No, function means we have a input and we have a output. So input is coming from the domain and output is coming from the range. So here input is an event. So if you take any function, it has input. Na? Input is an event. We apply the probability and it will give us a real number. So here we'll see the real number is basically so it is a positive real number. So that is the rule number 1. But before that, these are the rules. So before that this is a codomain. So it is a real number. If we take an event, if we apply the probability, it will give us a real number. That is the function. So is this
sir,
okay? Yes.
sir,
Yes, please, one by one.
sir, Sir, in third point, sir, probability of A1 union up to AN is less than equals to, there should be probability of delta, like, sorry,
This is
probability of omega. Sir, like on right
this
hand side, why is it written omega?
which one?
Sir,
This
in
one?
third point, P of A1 union A2 up to AN.
Oh, sorry. Yeah, no, no. This is not less than. This is. Oh, sorry. I should not use this probability here. So I. No, I. That was the point. Yeah, I mean to say, if we take n events, then if we take their union, they are all. That is also that is also a subset of omega. So that is also an event. If that is an event, then we can apply the probability on that.
Yes, sir. Yes, sir.
Yes, now it's correct.
Yeah, so I just overlap that. Okay, so that is an event. If we can apply this probability function on any event which having these three conditions satisfied, three rules, then we call that is a probability of that. So
Sir,
now it's okay now. Yes. Now this collection could be
sir,
finite or infinite. Yes, please.
so for third point you mentioned it should be countably infinite. Why is that so? Can you prove?
No, no. Countable infinite means we have a collection of say A1, A2, AN. So this collection, this set is countable. Now, if we have uncountable set, if we take instead of A1, if we take A alpha, A beta, I mean, which is not your bijection function from natural number to that. So that part we are not considering here. So this is a collection which is A1, A2, this collection is either finite, if it is finite like A1, if we have two events, A, B, if they are mutually exclusive, then also you can apply this because that is the rule.
So number of event will be
If you
countably
have
finite or infinite?
number of,
Event you said infinite, then it should be countably finite or
no, no,
infinite.
number of events is countably, number of events is countable. So in that case, we take, no, this collection has nothing to do with that. Na? This collection, say we have, you have to understand this. Suppose we have two events A, B, okay, and if they are mutually exclusive, then we can, the probability of A union B is nothing but probability of A plus probability of B. This is rule number 3. Instead of 2, if we have 3, then we can have this. So this way we can, if there are n, so that is finite. If there are infinite collection, but they are countable, like A1, A2 up to this. So, but we cannot. I'm not telling the union of A alpha, where alpha belongs to some say real number kind of thing, or some uncountable set. Sorry, real number. Anyway, some uncountable set. Then we may not able to define this measure. That was my point. But anyway, for simplicity, you just assume this we have a either finite collection of events or we have infinite collection, which is that collection, that set itself is countable set. A1, A2, we can have a sequence on that A1, A2 like this. Is this answer your question?
Yes, sir.
Okay. Yeah. So this is, if this is the three conditions, three rules, three axioms are satisfied, then we call our function is an our p function is a probability function. So from now onwards, we will take this definition as our yeah. So we take this definition. Okay. So I'm opening another page. Okay, good. So now we'll have some result using this. So the first result we'll see is like we have, so far we have defined this probability. Okay, so now can you prove this? The result, some result, some theorem, some lemma we are going to prove now. So can you prove this? Probability of an event mass belongs to this. How to prove this? We know that from axiom 1, we know probability of an event is greater than 0, but how to prove it is less than 1?
Sir, any event is subset of
So second
omega.
point. Using second point,
So
so
the
your
sample
number is 1.
Size of
Okay.
that set will be less than omega, hence always less than.
No, but you are using
Sir,
classical definition then.
like A is less than or A is subset of this omega. So if I apply probability, then probability of A must be less than
No,
probability
no,
of
but
omega.
see, I understand your intuition, but
Sir, we have to use the third point because whatever event we are taking, we have to take the union of all such events, and then that will be part of sigma only. Like that, the union of all the events will be sigma.
but
And
yeah, I understand, but somehow we intuitively in our mind we are running the classical definition. But as I said,
Sir,
we only have
can
these
I say?
three rules. Yes, please,
Sir,
please.
we will use a probability of A union A bar is equal
Yes,
to 1. Then we will split and it should be less
yeah.
than
So
1 as
basically,
by first
we
definition.
yeah, that is the thing. So this is a theorem. So how to solve this? So yeah, as you have suggested, if we take A union A complement, this is omega. Now we take the probability on both sides. Probability of A union A complement is equal to probability of omega. Now probability of omega is 1. Rule number 2. This we know. So rule number 2, rule 2 of our we just apply the probability axiom definition. And now by rule number 3, these are two disjoint set A and A complement. So you can split it up. Probability of A plus probability of A complement. This is nothing but 1. This is using rule number 3. Now what? Now this implies probability of A is nothing but 1 minus probability of A complement. Now A complement is also an event. So probability of A, rule number 1 we are going to apply. So this is must be greater than 0 because for A complement is an event. So probability of A complement is must be greater than 0. So if this is greater than 0, then this this must be less than equal to 1. So that is coming from rule number 1. So that means probability of this is done. So probability of A and this thing. Okay. Is this okay? Very simple. But we need to use that thing, that idea. Okay. Now another result we are going to prove is very simple result we are just discussing. Now if we have two events A, B, and if A is a subset of B, AB, and if A is a subset of B, maybe yeah, if it is proper subset, then okay. Anyway, then what is the result? Probability of A must be less than equal to probability of B. How to prove that?
Sir, we can write A equals to B plus B complement,
Okay.
and,
Sir,
and then we can solve it because then the probabilities of the
But we here AB are not, we don't know about whether they are mutually exclusive or not. So AB could be like this. So this is our A, this is our B.
So we can say P of A union B is P of is less than is less than equal to, no, it's equal to P of B.
P of
so we
A
can use
units.
P of
Yes.
sir, we can use A union B is equal to B and A intersection B equal to A,
Okay.
and then use the addition rule.
You are suggesting what? I mean, but then how will get this
So I'm
result?
actually saying that P A union
I
B
can
equals
understand A
to
union B is
the
equal to,
addition.
you are telling A.
No, sir, B, because B is the superset, and A intersection B equal to A, and then we use the addition rule.
Oh, sorry. This is not correct. I made a mistake over here because A is a subset of A is a subset of B. So A must. Sorry, I wrote a wrong
Yes,
picture.
sir. That's why.
Yeah. Sorry. So this is our B, and this is our A. A is inside B. Thank you. So yeah. Now it will be easier to understand. Sorry, I wrote a wrong picture. Okay. So A is a subset of B. So now
Yes,
how
A plus A complement
yeah,
equals to
so
B.
basically we can write B is equal to A union this part. This part we can write, I think, B minus A kind of thing. I mean this.
Yes.
I mean, if you are familiar with minus, otherwise B intersection A complement. Anyway, that is basically a B minus A. Now we can take the probability on both sides, and these two are mutually exclusive set. This is this set, and this is outside a ring set. So now we can use the probability rules to break it into two parts. Now this is a probability, so it must be greater than 0. So obviously P of B must be greater than equal to P of A. If it is 0, then equal, otherwise. Okay, so that is fine. So now we'll just try to get our classical definition with the help of this this our new probability definition. Okay, so how to get the classical definition? For classical definition, we have some assumption. So we have a random experiment and we have a sample space. Here we are having the sample space to be finite in order to apply the for classical definition, because now this is finite. And another thing, so if this is finite, we can just define the outcomes A1, A2, say n. We have say n outcomes. So if cardinality of this is say n, which is a finite number. So now we are going to prove the classical definition. So for that we need to assume they are equally likely. They are even the outcomes are equally likely. So equally likely means now we have a probability function, so we can easily define this. So equally likely means probability of each of these this thing like simple events, they are same. That is the what we mean by equally likely. Dot probability of n. So this is the meaning of equally likely. So under this condition, you have to prove that probability of an event is nothing but cardinality of A by cardinality of omega, and this is for all A. So that is what is called classical definition we have seen. So how to prove that? Any idea? We are going to show this using our, we only have the axiomatic definition. So any idea how to prove that?
So we will take a union of all.
Union of all. So A is an event, so which consists of some, say A is a collection of some of these AIs. Say if cardinality of A is M, then AI1 something like that, AI2, AIM. So they are all basically I1, I2 are all basically coming from some permutation on this A1, A2, AM. So we are taking the cardinality of A is to be M. So basically,
Sir,
please.
sir, we can first assume probability of each one to be some constant, let's say k, and then we can use the third theorem, that is like a1
Okay.
plus. We can take sum of all of them, like a1, a2, a3, and all of them constitute of sigma. And we
Yes.
can use the second one then, that probability of sigma is equal to 1, And then we can
Yeah.
use the third theorem that probability of union of all of them is equals to probability of A1, probability of A2,
Yeah.
and then we can replace everyone by K. Like probability of A1 equal to A2 equal to, we can replace by K.
So that is what you are suggesting. If we take this equal probability to be some alpha, then we can just use that because omega is nothing but union of this, union of A1, A2, dot 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 AN. Now if you take the probability, they are mutually exclusive. There's some singleton set, so they are obviously mutually exclusive. So then it will be sum of these probabilities, AIs, I is equal to 1 to n. Now this we have taken alpha, so this is n alpha. Now we know from rule number 2, this is 1, so this must be 1. So we have this alpha to be 1 by n. So this alpha is nothing but 1 by n. This we prove. Now, now again, A is nothing but the union of this. So I will take some space over here. Let me erase this part. Yeah, I'll take some this space. Okay. So now A is nothing but union of this Aij. So this is set. J is running from 1 to m. So now if you take the probability on this, so this is probability of this set, probability of union of Aij. J is running from 1 to m. So now we use the rule number 3, which is these are all mutually exclusive set. This is singleton set. So you can just write probability of, sum of that. So this is nothing but sum of this probability of Aij. J is running from 1 to m. Now these are all 1 by n. So this is basically m by n. This is what we are looking for, classical definition. So we prove the classical definition with the help of this thing. Any questions so far?
Sir, why did you
Yes,
define
please.
these two variables I and J? You mean I means which set and J means how many
No,
elements
we
are
have
there in
to,
that?
no, we have to get the elements of A, there are m elements. So if you don't like this Ij business, we can simply write this this A to be B1, B2, yeah. So A to be like B1, B2, Bn. But these B's are basically some of the AIs. So B1 could be some AI1, B2 could be AI2. That's why I use the index like that. But for simplicity, you can easily assume, you can easily take another symbol like B with the help of that. But since we have used A, so that's why we take the index. So B1 basically some AI1. We don't know now because that is some any A, any event A. Is this your question?
Yes, sir. I was confused with variable.
Yeah. So actually, I could use the BIs. Then I thought that we have used the A's, so that's why I use that. But yeah, so let us make life simple. So we take BIs. So B1, B2, BM. So this BI is basically sum of the AIs. It doesn't matter for our this proof. Okay.
Excuse me, sir.
Yes.
If I
Yes.
take
Yes,
if I
please.
take my sample set as heads as a set and tails as a set, and another set as heads comma tail. So there is no way that A1 union A2 changes to probability of individual sum, right?
What is your
Because there is an
experiment?
intersection.
What is your experiment? Tossing a coin.
Yeah, yes, sir.
You
So
know,
my
you are
sample set
talking
would be,
about the power set. You are just reconsider once.
Yeah. So what is the question? I can just. So if you are tossing a coin, then we have two we have two outcomes, H and tail, and then events are any subset of this any subset of this omega is an event. So how many events we have? We have either H, we have this is omega and null set. So this is a power set. So this any member of this set is an event. So any member if you take from this, we can talk about the probability of that. Okay. I didn't get your question actually. Is this your?
Yes, sir.
You just feel free. I mean, see, I mean, question may not be so. See, this is the beginning, so doesn't matter. I mean, sometimes I also can ask you some bad questions. Don't be shy. Just come out. In any way, there is an advantage of online course. We cannot see the face to each other. Please, please.
Sir, in this power set, the probability of all the events are not same, na? The
Probability of
probabilities, all these events will be different.
this one.
No, sir, in the power
Since
set, in the power set. In the power
that
set, the
There are
that
4
probability.
elements.
Oh, this one, no, we cannot define the probability on this power set. No? We have to
Yeah,
define
yeah,
the probability on the events. So that doesn't matter. I mean, that will depend on the which definition you are using and which way. So they will be, so far we know they will be a real number basically.
yeah, okay.
That depends on the, if we use classical definition, then we know all the picture. This is half, this is half, this is 1, this is 0. Okay, so this we know.
So how can we relate here the equally likely? We can't relate it in the power set, na, sir?
No, we can't relate. For classical definition, so far whatever problem you have solved in your class 2, everything we use some. So everywhere we use the classical definition. That is the classical probability theory. So there we use the equally likely. So there, here in general we cannot say. We cannot say that we have a coin which is having half probability. But if we want to apply the classical definition, then we have to assume that these two are uh, equally likely.
So what I feel like equally likely word is defined for the outcome, not for the event. Yes.
Not for the event, it is for the outcome. But outcomes are outcomes are the simple events, no?
Sir, on
Outcome,
simple event we can relate it.
yeah, outcomes are simple events. So this is, if we take the H and tail are the outcome, they are also the simple events, singleton events.
Okay.
Okay, so we can move. Okay, so basically we just going towards some what is called total probability rules and Bayes theorem. So before that we can just have some something, if we are some random experiment again, if we are tossing say 3 coins or a coin 3 times, 3 coins. So then at the same time, if we are tossing 3 coins at the same time, or we are tossing a single coin repeatedly under the same condition, identical conditions, okay, then what will be the outcomes? What will be
So
the
there will
outcome?
be 8.
There will be, so this is actually, there is a tree, you can see. If we have tossing a 1 coin, then we have HT, and then again if we tossing this, then this is again HT. Just a tree structure, we can get the outcomes. HT, this is 2 times, another times HT, HT. This one is also HT, HT. So this is the, so omega is nothing but we take all, so H, all three are heads, then H, so all the path from leaf to the root, these are called leaf nodes of that. So T, H, then H, T, how many possibilities? What is the number?
Eight.
8 possibilities. Yeah, so these are all outcomes of this. Anyway, we'll discuss more on this tossing business slowly. Okay, now go to the another. Any question?
How did you made this tree structure? Like
Yeah,
the
just
first row was for one coin, then second for second coin.
yeah, I am just opening that. Now, if you are tossing the coin once, then we have two possibilities, H and T. Now, if you are tossing again that coin, then we have two. Every time if you toss a coin, we have only two options, H and T. So that way we are tossing 3 times. That's it.
Like we have three coins, that is one case, and
No,
tossing one coin for
one
three
coin.
case.
Suppose we have one coin, we are tossing 3 times.
Yes, sir. Then its structure is correct.
Yes. We have one coin, we are tossing 3 times. But that is same as we have, we can wait and then we can toss, then we can just, this is the structure to get the events basically. Okay, so now we'll discuss some of the properties using on the probability. So first, this is the addition rule. Okay, so we have a random experiment, and then we have omega, and then we have already defined the probability function on that. So now we take two events, any two. I mean random. I mean it should not use random one. We take two events AB. Now we are interested to know their probability of their union. So we are interested to know probability of A union B. You got my point? We are having two event AB.
Yes, sir.
We are looking for what is the probability of union B. So now we can have this picture which we draw earlier. So this is our picture. Okay, so what is that?
Probability of A plus probability of B minus probability of intersection.
How to prove that?
So from the Venn diagram, we can say.
Sir, we can take three mutually exclusive events like probability of A minus A intersection B, and
Okay.
probability of B minus A intersection B, and probability of like A intersection B. And then if we add all of these three, then we can get it.
Yeah, so you are suggesting this one. We identify this
Yes, sir.
C portion B minus A intersection. So these three sets are mutually exclusive and they are basically A union B. So A union B is nothing but A, so this is X, this is Y, this is Z. So X union Y union Z. So now we take the probability. So probability of these three mutually exclusive set. So this is probability of A, probability of B, probability of AB. So, but then probability of A minus A intersection B plus probability of A intersection B plus probability of B minus A intersection B. But we are looking for something else.
But sir, now probability of A minus A intersection B will be probability of A minus probability of A intersection B.
Okay,
Like,
so you are suggesting that, so this part I am using. So you are telling that A can be written as A, no, what is it? Yeah, so this part and this part. If you just consider the A is consists of this part union this part. So this part is A minus, which is not a good expression, this part and union of A intersection. This is what you are suggesting, right?
yes, sir.
So now these two are mutually exclusive. So probability of A is nothing but probability of A minus A intersection B. You should be careful about this bracket, okay? Plus probability of A intersection B. So now you take this we got basically probability of A minus probability of A intersection B. Similarly, this part also you can just take this part, these two union. So probability of B minus probability of A intersection B. So if you combine this will basically get in probability of A plus probability of B minus probability of A intersection B. So that is our probability of A plus probability of B minus probability of A intersection B. Okay, so this is our addition rule for probability. Now if AB are mutually exclusive, then we got the rule number 3, then this will be null, empty set, and then this probability will be 0. So this we got this. Now can we extend this for 3 events, ABC, or more than 3, 4 events?
Yes, the inclusion exclusion.
Yeah, so we can just have, yeah, can we just try to write for 3 events, ABC. So probability of, sorry, yes, so probability of A intersection B, sorry, union B, union C. So this is probability of A plus B plus C, then we
Sir,
have
Minus
minus
probability.
A intersection
intersection of
B
two
minus
two.
B intersection
yeah
C.
all the
Minus of
two.
intersections, taking two
Yeah,
at a time.
so I take minus common, so you can just take it like all the A intersection C
and
and
then
then
plus
And then add
then,
then
intersection of
plus
all ones.
intersection of all.
then plus
Intersection of all three.
all three. Yeah. So this we can continue up to D. So in general, can you try to write that? I mean, like probability of AI. This I is equal. Is it work for infinite? In that case, we need to prove this. How to prove this type of statement? Any method you know?
Induction.
Yeah, mathematical induction we can
Induction
use.
method, PMI.
Yeah, so we can use the mathematical induction to prove this. Anyway, so this is n, then we have a minus I not equal to j, then probability of A intersection AI intersection AJ. So and IJ is lies between 0 to then alternatively we have a 3 combination summation of IJK. They are all not same and they are all coming from this this thing less than equal to, okay, probability of AI intersection AJ intersection AK, and then we have minus. So at the end we don't know the n, so we need to write minus 1 to the power n minus 1 p of A1 intersection A2, sorry, dot 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 intersection an, because we don't know n whether it is even. So this is, anyway, this is a general expression and you can just try to prove this. Okay, so next we'll talk about the conditional probability, but I think we should take a break for that. Okay.
Excuse me, sir.
Yes, please. Any question?
Excuse me. Sir, can you go to the slide in which you mentioned the sample space as heads and tail? I
Just a
think
minute.
three
Yeah,
sides
now
black.
previous sample space and head and tail. The power set?
Yeah, yes, sir. That one. Yes.
Yeah, I'm trying to open. Is this the one?
Yeah, yes, sir.
Yeah,
So
please.
if I choose an event A, which is a
Hmm.
set of H and another set H comma T.
Can you repeat again? If
So
you choose
if
a
I
event
choose an
A,
event A, which is
uh,
a set of heads and head and T,
1 minute, I guess.
nothing but the first term and the third term.
Just a minute. So your event is A is
Yeah, heads is a set.
H.
Yes, sir.
Only H.
And H comma T, a set of H comma T.
No, I'm not getting you properly. You are telling H is an event.
So previously we have chosen that A can be chosen as any subset of
Any subset
sigma,
of
right?
the power set.
Yeah,
Sorry, any member of the power set. So any subset of sigma. So how many
so
subsets
I
are
can.
there?
So there are four, right?
4 subsets. So either you choose this, or you choose A to be T, or you choose A to be H and H union T, or you choose A to be phi. Now you may be trying to confuse with the making subset of this power set. That is not an event. Are you doing that?
Okay. Yeah, I was having that.
No,
Yeah.
don't,
He
no,
was
no. That
trying
is,
to combine two
yeah.
events
No.
simultaneously.
Don't confuse with that. We said that any member of this is an event. If we said A is an event, if A belongs to the power set of this power of omega, not a subset of power of omega. Here it is a subset, but here it is a member. So forget about power set. Just think event is an any subset of omega is an event. We have a random experiment, then we have corresponding omega, and any subset of omega is an event. Now I got your confusion. You are trying to make the subsets using this power set. No, that is no, that is event is a member of the power set. I just use power set because to if we are looking for a function, na function is a some mapping from one to so P is a function. So to denote what is the domain, that's why I defined the power set. So P function is taking an event. So the events are coming from this power set. But don't confuse that you will make this subset with the from the power set. No. So just forget about this power set business. You
Sir,
take the event to be a event is any subset of omega is an event. Okay.
so please open
Okay,
the
got it.
board of where you wrote the formula of unions, like last formula.
Last word. Okay. Is this one?
Yes,
Okay. So we can any question you have here, or you want to just take a note?
yes, you're noting.
Okay. So we can take a break for 5 minutes.
Okay.
Okay.
Yes, sir.
So I'm just stopping the recording. Just a minute. Yeah, I just stopping the recording. Stop. Stop the recording.